So what I'm going to do for these next few tutorials is work through one of these FSL examples, which I think will be useful. It'll illustrate some of the concepts behind it and give you a good understanding what DTI data looks like and how to analyze it in FSL. So for this, make sure that you just Google FSL course, click on the FSL course link that comes up. I'll also try to post this below in the box. And go down to data files and download file 2, which is diffusion data. Okay. And also for right now, I just want to show you, if you do have a single, say, DTI data set, the first thing you want to do is you want to convert this. And luckily enough, it's very easy to do this with something like the MRI-Cron DICOM to NIFTY tool. So if I open up DICOM to NII, GUI, and I open that up, remember that you can easily convert DICOM images to neuroimaging files by just clicking and dragging all your DTI files into this DICOM to NI GUI right here. So these are all DICOM files just from a sample subject, and if I selected all of them, drag them in here, I've already converted them, what you would get is a BVAL file, a BVEC file, and the DTI, the diffusion weighted image. Okay, so BVAL, BVEC, these are simply values that are going to help you determine both the direction of diffusion and also how much diffusion is going on in a specific voxel or along a specific tract. Okay, first thing you'd want to do, again this is just a very brief overview just to get you grounded, get your feet wet with how to do DTI data. The first thing is you would actually do something very similar to motion correction, which is called eddy current correction. So you just upload in this your diffusion weighted data. Okay, simple enough. Give it an output, reference follow me if you want to, it doesn't matter that much, and then hit go. It takes a long time, I've already done this, so I'm not going to review this. But after you do that, the next step would be to do DTI fit, which is reconstruct these diffusion tensors, giving us a sense of where the predominant direction of diffusion is going along these different fibers. For this, I click specify input files manually. Diffusion weighted data, again, this is the output from this conversion tool. I use DICOM to NI GUI, but just make sure that you're selecting this diffusion weighted image. It's going to automatically fill in this output base name. That's fine for me. And here, one other thing I should probably mention is that I also created a mask, just like what we do through BET. Very simple. There are other tutorials on this that I've made before, so consult those if you have any questions about that. It also wants the BVEC file, which again has been very easily provided through converting it through DICOM to NI GUI, and also the B value files. Okay, once you hit go, it just does that for every slice. It goes pretty quickly, and once this is done, we can see very easily what a typical DTI diffusion tensor fitting looks like. So just to get you familiar with how you go from this raw DTI data to constructing something that looks like what you would see in, say, a DTI paper. This is only for one subject, which is not interesting, unless you did one subject at one time point, then at another time point, say after an intervention or something. But for right now, we're just going to look at a single subject to look at these tensors. So first of all, notice that there have been a bunch of files output with DTI prefixed to them. DTI FA is what I'm going to load up first. This is the image of fractional anisotropy, which in itself isn't going to look too much different from a typical anatomical data set, or just a really high resolution T2 weighted data set. I'm also going to add one of the principal vectors, in this case, let's say DTI view 1. And once I've done that, go down here and click on this eye, this eye next to the eye. I like to have fun sometimes. And for this, image type is going to be diffusion tensor, and we're also going to display it as RGB. Okay, so now this is looking a little bit more familiar, and we're going to modulate it by the DTI FA, the underlying fractional anisotropy data set. So this already looks pretty similar to what we would see in a typical paper. This is just for a single subject though, doesn't tell us that much, but what we can see is that after we've done this very basic DTI pre-processing, we have different color codings for where the direction of diffusion is. So for red, that's diffusion primarily along the left, right, or X direction in fMRI terms, or just neuroimaging terms. right? And that makes sense that it seems the heaviest along the corpus callosum because those bundles of white matter tracks do indeed run primarily from left to right. In some place like the internal capsule, you see more blue, and that is diffusion that's primarily going from head to foot or in the Z direction, right? So the internal capsule, remember, that carries information from things like primary motor cortex, primary somatosensory cortex, both efferent and afferent nerves communicating with the rest of the body and the central nervous system and peripheral nervous system. And lastly, green is primarily diffusion going from say the back of your head to the front of your head, or in other words, the Y direction. Okay, so things like the fascicles going from the back to the front, those are primarily represented by green. The first step in DTI analysis is similar to what we do in any sort of fMRI analysis, and that is we try to correct for any sort of distortions or any kind of motion that went on, right? So there are some analogs to DTI analysis that we see in fMRI analysis, if you're familiar with that. So, for example, in fMRI data, sometimes we acquire what's called a field map, and this gives us a sense of where there might be distortions in the magnetic field. And if we have those, then we can basically take the reverse of that and try to subtract that out from the image to get rid of all that distortion. So this first step that we're going to do here is called top up. It's, from what I can tell in the latest version of FSL, it's still only a command line tool. It's not available through the graphical user interface, but that might change soon. So we're going to be using that to essentially get rid of any sort of distortions that happened when we were acquiring a DTI data set. So let's take a look at the data that we have. Right now I'm using the FSL tutorial data. I've downloaded it. It's in this file path. We're in FDT1/subject1_preproc. So what we have in here, we have BVALs, BVECs, that's just the stuff you'll need to do your DTI analysis. We also have the diffusion weighted data set and this thing called ACK params. Okay, so just briefly to just look at ACK params, this gives you a couple of rows, and this number right here in the second column that tells you whether this was acquired in the anterior to posterior direction, the posterior to anterior, and this last column is the readout time from the first echo to the last echo. So not to get too technical, it's just something you'll need from your scanner technician about when this scan was acquired to get a sense of how to unwarp these distortions when you apply top up. So the first thing that we want to do, and also notice that we have a couple of things here. We have the diffusion weighted data set. We also have this no difference posterior to anterior acquired data set, right? So we want both the posterior to anterior acquired data set and the anterior to posterior acquired data set. So how do we get that other one? Well, we're going to use this thing called FSL ROI to basically extract the first frame or the first image of our DWI data set. Okay, so I'm going to extract it from DWI data. This is also called no diff. It's basically our reference volume, and we're extracting it from the very first image of that data set. Once we have those, we're going to merge those together using FSL merge, and we're going to call this anterior to posterior underscore posterior to anterior B0, which is essentially our reference image. And we're going to combine no diff and no diff in the other encoding direction. So before we go on, let's just take a brief look at what those two images look like. So if we load up, let's say, just the no diff data set, if you just look around this, if you have a pretty good idea about what functional images should look like, some of this stuff may appear a little squashed or elongated in certain places, especially in the very posterior and the very anterior parts of the brain. We can add our no diff PA, and we can toggle between the two by double clicking on this eye icon right here. And you'll notice that between the two there does seem to be a lot of variability. Essentially both of these give different information about susceptibility artifacts during the DTI acquisition, and we're going to try to correct for those. So now that we've merged both of those into a single data set, we have what we need to run the top up to give us some estimates of where all these distortions occur. So this first command, top up, is just the estimation. There's also apply top up, which is another command which will actually apply it and try to unwarp it. So top up requires a couple arguments. The image in is going to be this AP PA B0 image that we used to, that was a combination of these different encoding directions. And also it needs this parameter file. Okay, remember, this is something that, comes with this tutorial data set, but this is something that you will need to get on your own from your scanner technician. Okay. Config, this is something that will be output, I believe. I don't think it's an essential command, but it's what's listed in the tutorial help. And the output data set, we're going to call that top up APPA-BO. Okay, so this thing actually takes a while. It's already been run. I just want to show you what the command actually looks like. And all this stuff is actually in this pre-baked folder. So this had all the top up and all the edit correction applied to the data set. So we're going to take that first just because we don't want to wait for all this processing to take place. So we're going to take this data set of have the top up applied to it and put it up in here. So if we open up FSL view and we take these images that have had a top up applied to it and have had all these distortions basically mapped out, you'll see that this looks a lot like a field map, which in both instances, both with the field maps and fMRI and with these maps that we have right here, these are estimates of the distortion across the image, right? And so basically we're going to try to do the reverse to undo all these distortion effects to get a cleaner image. Okay, so lastly, now that we have that, we have what we need to go forward and just run the eddy correction, which is kind of like a motion correction step. But just to show you how this has affected our data, how it has corrected for some of the distortions, I'm going to run the apply top up command. So similar thing, it needs a couple of different images. So the no-diff dot underscore PA, and also the top up map, which is essentially an estimate of all these distortions and where they occur. Okay, which is APPA-BO. Data in, again, is the ACK params that we had before. And in index, we're going to make that 1 and 2. And lastly, an output file, which will be hi-fi underscore no diff. This doesn't take too long, but this is a step you won't usually run in your processing stream because you just need the estimates to use with another tool, and you basically can just skip this step. It's not essential, but I just want to use it to highlight what this will look like after all these distortions have been corrected for. And once that is done, we can open up FSL view again. Open up this hi-fi data set that we just created. And also compare that to both of those files which had not had any distortion correction yet. Okay, so if we look at that, if we just look at one first, this hi-fi no diff, this is the corrected image after top up has been applied. Notice if I look at one of them, it appears a little bit elongated in certain parts of the brain, and the other one it looks a little bit squashed. This is basically taken both of those into consideration, and it's looked at this estimation of discrepancies file, or this estimation of distortions file, and used it to correct these images. So that's a very brief overview of top up. Again, if you've done field mapping and field unwarping, it's the exact same concept. It's really the same thing that's going on. We're just applying it to DTI data. And we're going to use that in the next step for something called eddy correction, which is like motion correction for traditional fMRI analysis. Now that we've run top up, we have an estimate map of where any susceptibility distortions are in our data set. And we can use that now in combination with a tool called eddy, which will also apply something akin to motion correction that we would see in traditional fMRI analysis. So all we have to do here, first we have to create a mask using FSL's BET tool, the brain extraction tool. And so this is the command. I've already run it. These defaults are usually fine. So fraction intensity threshold of 0.2. This is just something that's toggled to either be more conservative or more liberal in how much brain it tries to extract. But usually this is a pretty good compromise, 0.2. So that's what I've done so far. And after you have that, this is the EDI command. I'm not going to run it because it's already been run, and we're just going to look at the output. But in a nutshell, it's going to take in this DWI data set that we got from the scanner. It's going to apply this mask that we just created using BET, and also this index command it's basically just a text file which has a 1 wherever these acquisition parameters hold. So typically it'll hold for every volume in that DWI data set, so we'll have a 1 for each row for each volume in that DWI data set. BVEX, BVALs, those should be pretty standard. And also we have a couple of defaults here, FW HM or any sort of smoothing. Typically we set that to 0 because we don't want to do any smoothing in this step. And also this FLM quadratic, I don't want to get into technical details. I don't completely understand it, but they say it's a good default and that you typically won't need to change it at all for your purposes. This top-up, remember, is what we ran in our previous tutorial, which is an estimate of all these susceptibility or artifacts that we have in our DWI dataset. And lastly, we output it as these EDI unwarped images. So again, we have this all in this pre-baked folder right here. And if we copy it all into here, we can look at it in FSL view. So again, we're just going to do a before and after comparison. And our first standard of comparison is just the normal DWI dataset that we have. Again, this had a little bit of smushing and some elongation just due to different artifacts. And now we have this EDI unwarped images file. And so if we toggle between the two, not only has it corrected for any distortions, but also it's done the equivalent of motion correction that we see in fMRI data. So if we go into movie mode, that's kind of difficult to see. Actually, I mean, you see some bright spots because it's affected by, I believe, what the peak intensity is in that particular volume. But if we set this to something a little bit lower, what you would see is that not only are the distortions corrected, but we've also corrected some other things as well. That actually probably was not very illuminating or useful, but you can use this movie mode to try to see how different volumes have been changed as a result of both top-up and by EDI. That demonstration kind of failed spectacularly. Anyway, so that's EDI. Those are the two basic pre-processing steps that we use for DTI data, and then the next time, or the next step, will be actually fitting tensors to this image.